This is the centripetal force apparatus. And as you can see, it's pretty basic. We have sort of the center pull, which is supporting all the components. We have this top arm here, right, which drops down, and that's where we're gonna be hanging our mass or the bob from, right? Now what connects these two things is this spring here. So it's important to remember that this spring is really, really important, right? It doesn't really do anything, and it's not active in the lab, but what it does do is it sort of keeps this bob tightly bound, right? Which allows the spring to push it back this way when we rotate. What that does is it emulates a centripetal force, right? It's also important to remember that this distance here, our radius, that's always gonna be fixed. So essentially what that does is it keeps our centripetal force fixed for all the different trials we're doing for this lab. Now if we take a closer look, we see this little scale here, right? And again, as we rotate this, what's gonna happen is we're gonna have a tendency for the spring to push back that way, which emulates the centripetal force. However, because this bob isn't completely attached to this system, right? Because it's essentially independent of it, what we'll see is this is going to also be subjected to the centrifugal force. So as we rotate, what we'll see is this bob has a tendency to slide outwards, right? So you have the centrifugal force acting outwards while you have the centripetal force acting inwards. What we're concerned with is the centripetal force, right? We want to know what's causing this spring to contract and therefore the force acting inwards. What's the consequence of that? It just happens to be the centrifugal force, the false force. That's something we're less concerned with. However, it does play a crucial role in figuring out the linear mass or the linear force. So as we rotate this, we'll see this bob sort of stretch outwards. What we're going to do is make use of that when we translate that to our linear force. And we'll see again that spring stretch outwards. Our goal for this lab is to essentially find a measurement or calculation for the centripetal force, which is our F theoretical, and compare that to our linear force using F equals ma. That's going to be our F experimental. So again, because this stick here is fixed, or this radius is fixed, the centripetal force that's applied by the spring, right, the thing that emulates the centripetal force, is always constant. Because we are choosing selectively what our mass will be and what the radius will be here, right, the radius of our circle, we know that there's only a few variables that can change given our equation. And one of the things that's going to change, because those things are fixed and because those are selected values, is going to be our acceleration. However, we're not measuring our acceleration directly. Instead, what we're measuring is the velocity, and we're measuring our velocity given our period of rotation. So suppose you had a stopwatch, right? You're at some given mass at some radius. You can actually rotate this some number of times. In the lab, it describes 25 times, and that's going to give you some time total for 25 rotations. If you take that divided by 25, then you will get the period, the time for rotation. And given that, and given the radius that we're given, right, here it's 15, we can essentially figure out what velocity is using one of our equations, which is 2 pi r divided by t period. Now that we have that, we can directly calculate what the centripetal acceleration is, and thus what the centripetal force is.